Welcome to Astro 101, the sun and its neighbors. I'm Professor Barth Netterfield. For this class and for the next one, we're going to come back closer to Earth and talk about the kind of astronomy that we can see ourselves all the time, even in the city. So what are some of the sky things that we can see every day? Well, there's the sun. Sun rises and sets, and that has something to do with something. I guess there's longer days in the summer and shorter days in the winter, so that's cool. We can understand that. Then there's the moon. The moon is in the sky, and sometimes you see it in the daytime, and sometimes you see it at night, and sometimes it's a full moon, and sometimes it's a partial moon. It'd be nice to make sense of that, so we'll try and do that, probably next class. And then there is the stars. Look at the stars at night, and you see the stars, and you see a pattern in the stars, and you come back some other time when the pattern is different. Maybe it's moved, maybe it's a completely different pattern. So it'd be nice to make sense of that as well. So let's dig into it and try to understand these things about astronomy that we see every day, never really paid attention to. So to start with, I'm going to go and talk to a special guest who is currently at June 20th, 2020. Let's take a look. Professor, good to see you. Well, thank you. I am reporting to you today from on top of Centennial Park Hill on the edge of Mississauga, where we are watching the sun just going down below the horizon on the summer solstice. This is the day of the year where the sun sets the farthest north. It's also been the longest day of the year and the day in which the sun got the highest. Is that true everywhere on Earth? No, in fact. In the southern hemisphere, it's completely backwards. Today was the shortest day of the year where the sun got the lowest. Consequently, here in the north, this is the first day of summer. In the south, the first day of winter. Beautiful day? Oh yes, it was a gorgeous day. Blue sky, clouds, not too hot, and a very auspicious start of summer. Well, that was cool. Thank you. We had a question for you, actually. How is things going with COVID-19 there in the future? Better? I see. I mean, things opened up, phase 3, you know, that's great to hear. On the other hand, the numbers are going up and it may have to close down again. I'm so sorry to hear that. So there's rumors of a vaccine in the horizon. Maybe that'll help. Okay. I mean, hard to say. Now, and there goes the sun. Well, talk to you later. Nice jacket. So, sunset, June 20th, furthest north of the year, longest day. So, let's see what happens if we come back a couple months later. So, I've got another guest who is actually on, I think September 11th. So, let's check in with him. Me. Hey, great to talk to you again. Yeah, it is indeed. How are things going? You're watching the sunset. Indeed we are. It's September 11th, 2020. Sunset today is at 7:34 p.m., 6 degrees north of due west. And there it goes. Well, cool. Now, back on June 20th, when you were up on the mountain, it set 34 degrees north of due west at something like 9 p.m. So, over there. Yeah, so it's moved a lot. Indeed it has. So it's too bad we can't get footage next week at the fall equinox, or even better, in December at the winter solstice. Well, I guess we could just wait and film it later. Yeah, but we got to get this done. Classes are starting. Yeah, well, we can look up in the tables and know that in the winter solstice on December 20th, the sun will be setting at 34 degrees south of due west, more like at 4:30 in the afternoon. So over there. Yeah, that'll be pretty interesting. Well, thanks a lot. Well, that was pretty cool. So what have we got here? We've talked here about 5 different dates. We had the summer solstice back in June, where Professor Netterfield was. The sun set at 9:02 p.m., 34 degrees north of due west. So that's the arrow showing the sun setting there. Then a couple months later, on September 11th, 2020, that was for me last Friday. For you, it was a little bit further ago. The sun set at 7:34 p.m. at 6 degrees north of due west. So over there. So you can see how much the sunset moved between those two dates. So from here all the way over to here in a couple of months. And then the prediction is that by the fall equinox, which is around when you're going to be watching this video, the sun will move another 6 degrees over to here. And then by the winter solstice, it'll be 32 degrees south of due west. So way off over here where you can't even see it. So this is pretty interesting. Now, what do I mean by degrees? That's something I probably should explain, right? So let's talk about that. Imagine you've got two lines that come together to a point. We can talk about how far apart these two lines are. We call that an angle. So that the angle is right there. The angle is kind of like the distance between these two lines. It's not really distance, but it's an angle. Yeah. Okay. So how do you measure an angle? Well, you can measure it with, for example, a protractor. So here we have a protractor, and the protractor is we can use to try and measure the angle. Maybe you've seen these before when you were in elementary school or something. You line up one line with the 0 line, and then you see where the other line goes, and you measure along it. It's this angle right here is, in fact, 34 degrees. You can measure that. 30, 31, 32, 33, 34 degrees. Okay, cool. That's an angle. We can try this again with a different angle. Here we have another angle. We want to measure the angle between these two lines. So how do we do that? Do this again. Put the protractor in. All right, what's that? That is 25 degrees? 24, 25 degrees. Look at that. 25 degrees. 20, 21, 22, 23, 24, 25 degrees. Cool. So we're getting the hang of this. We can measure angles. Let's try one more. There's two lines. Measure the angle. Bring the protractor in. Boink. All right. And this one is 118 degrees. Cool. So angles. Now, I was saying, giving the direction where the sun was. So how do you describe directions? There's kind of two ways that you hear sometimes. The first way is this. You say how far the angle is from some cardinal direction. So the cardinal direction here is west. And we would say, in this case, that the angle, the direction of the sun, was 34 degrees north of due west. So we'd say, use due west, and it was 34 degrees north of there. But there's another way of describing it. And instead of that, you can say, well, that's kind of long. And actually, the second method is much more common. You can say, okay, let's define north as 0 degrees. So that's 0. And therefore, east would be 90 degrees. So 0, 90 degrees. Okay. South, 180. 0, 90, 180 degrees. West is 270. And so we can measure the angle between north and the line going around this way, like this, and say that that is 304 degrees. So you can either call that 34 degrees north of due west or 304 degrees. Now, normally when you look at a table of like sun directions, sunrises, sunsets, moonrises, moonsets, this is how they'll describe it. It's called an azimuthal angle. It's the distance from due north. So 304 degrees is the same as 34 degrees north of due west. So going back to this table, here we have at the summer solstice, the sun was setting 34 degrees north of due west, or 304 degrees. On September 11th, it was setting at 6 degrees north of due west, or at an angle of 276 degrees. By the fall equinox, it'll be at 270 degrees, which is due west, or at the winter solstice, it'll be down to 238 degrees, which is 32 degrees south of due west. So there we go. The sun. The sun moves during the year. It sets further north in the summer, further south in the winter. That's true for the northern hemisphere. In the southern hemisphere, it's going to be different. Okay, so let's think about the stars. Now, what do the stars do? We've been thinking about the sun. What about the stars? So we were up on vacation in Thunder Bay in August, and while we were there, I set a camera out to take pictures of the sky every few seconds throughout the night. So here we go. Every few seconds, it takes a picture, and we see the sky rotating. Now, it's kind of jittery. It's not perfect. There's problems with the internet. Occasionally, the lens got foggy. You had to clean it, so you see a little bit of motion there, but it gets bright again. At one point, you see a flash of lights. That was some good friends of ours coming back from getting engaged, which is pretty exciting. J&J forever. But nonetheless, you get the picture. You can see the stars rotating around this point right here. This star right there, that's called Polaris. It happens to be very close to the point in the sky that all the stars rotate around. So as the night progresses, the stars rotate around that point. So that's pretty cool. We can take this and we can actually, instead of looking at this series of pictures that I took at great pain, we can look at instead a planetarium program. This is a planetarium program called Stellarium, and it is simulating what I should have seen from Thunder Bay at the same time on the same night. Namely, all the stars rotating around Polaris. It's the same patterns of stars going around. In fact, when you look at these back to back or side to side, they look the same, except this one doesn't have all the flickers and jerks and stuff. They look otherwise basically perfect. So what are we seeing here? We're seeing all the stars in the sky rotating around this point. This point is basically due north. In fact, north is the direction of that star, more or less. So, or at least the direction of where the stars all move around. It doesn't move around exactly around that point. That point moves a little bit, but it's pretty close. So that's really cool. So there are programs, people has been spending millennia tracking the motion of stars to increasingly high precision. So we can write programs that will exactly predict where all these stars are. And in fact, the models that go into, we're going to describe the models that go into these programs in the next few weeks. But the point is, these programs can do an incredibly accurate job in predicting where you should see stars and when. So the stars at night rotate around that point. Sunrises and sunsets, stars rotate around that point. Let's take, now that we have a program, Stellarium, that we can use to predict what happens anywhere in the sky at any time, we can go and take the same program and run it in a different place. Let's take the program and run it in Toronto on the summer solstice. Now, so this is imagining there was a field in Toronto. This actual field's in France, it turns out, but let's pretend it's in Toronto. What do we see? We see at night, looking due south, looking here, due south. We see the sunrise go across the sky and then set. We see stars rotating around a point down here somewhere, below south. So the stars are all rotating around a point down here. We see the sunrise, go through the sky, and then set. So that's what we should see in Toronto in June 2020. So all I did is, earlier we saw me taking a picture of the sunset from Centennial Park Hill. But this is what happens during the day and during the night. So let's fast forward this. Instead of June 2020, let's go to December 2020. December 21st, 2020, we see the same sort of thing happening. Stars rotating around a point down here, the sun rising and then setting. But, so it's still rotating around the same point down here. We see different stars in the sky, it looks like. But the biggest difference is that the sun doesn't get near as high. So we can compare these two times. In the summer, the sun is way up here. In the winter, it only gets up to here. In the summer, the days are much longer. In the winter, the days are much shorter. So what's the difference between the summer and the winter? In the summer, daylight is longer, darkness is shorter. That's the thing number one. Thing number two, the sun gets higher in the sky. In the winter, the days are shorter and the sun does not get as high in the sky. What do I mean by high in the sky? I don't mean further away. I mean a greater angle from the horizon. So this is 70 degrees high. This is only 23 degrees high. Now, it turns out this makes a really big difference. It makes a difference in that the days are shorter. That's important. But it also makes a big difference because when the sun is more close to a 90-degree angle, when the sun is closer to straight up, it deposits a lot more heat than when it's at a shallow angle because the light is spread over a longer area. So in the summer, the sun is higher in the sky, it's closer to straight up, which means that it's giving more heat to the ground. In the winter, the sun is much lower in the sky, doesn't get as far away from the horizon. The angle is shallower and therefore deposits less heat. This is the biggest effect on how warm it gets in the summer. So why do we have seasons? Because in the summer, the sun gets higher in the sky and the days are longer. In the winter, the sun does not get as high in the sky and the days are shorter. So that's cool. Now, why does this happen? Now, when you looked at the previous thing with the stars rotating around Polaris from Thunder Bay, we were seeing it, well, even when you come back here to these pictures here, it really feels like the sky is rotating, right? The sky is rotating around some point here, and the sun is moving, the sun moves up, the sun moves down. It looks like the ground is fixed and the sky is rotating. And you can think of it that way. I mean, people have thought that way for thousands of years. It turns out that that's not a very good way to think about it. It's much better to think about it like this. here's the sun shining, shining at the Earth, and the Earth is in fact rotating. So what we have going on is over here, it's nighttime. This line is sunrise, and then over here it becomes daytime. So there's the sun just rose in Brazil. Okay, so over here is night, over here is daytime. As a point on the Earth moves across this line, it goes from nighttime to daytime. This explains why it's daytime at different times on the Earth. But I mean, you could think of the sky going around the Earth. You can think about the Earth rotating. Well, if there's a difference, right? If the Earth is rotating, you should be able to feel it rotating. Except it's rotating really, really slowly. So our rotation sensing things in our ears or whatever are not near sensitive enough to detect the Earth rotating. It goes around once per day. That's really, really slow. But it turns out there are instruments that are sensitive enough to measure the Earth's rotation. For example, a very good gyroscope can do that. We have some very good gyroscopes at the lab, and we can measure the fact that, yes, in fact, the Earth is rotating. So this is the correct view. It's okay to think about the stars rotating around the Earth, but then it becomes really complicated because now you have to explain why the gyroscopes are measuring the Earth rotating. This is a much better way to describe the way the universe works. The Earth itself is rotating. We can measure that. So let's look at this picture here. Here you have the Earth rotating. Now, it's actually a little bit more complicated. The Earth is rotating around this yellow line and then is orbiting around the sun on this blue line. Now, what you see happening here, which is pretty interesting, is the axis of rotation, the axis around which the Earth is rotating, is tipped relative to the ecliptic plane and is always pointing in the same direction. So if you were standing at the North Pole and looking straight up, you would see Polaris, and throughout the year, it would always be in the same place and never move. Okay? So that yellow line is pointing at Polaris, the North Star, always. Summer, winter, throughout the entire year. And as the Earth is rotating around the sun, that line is continuously pointing at Polaris. So let's try and look at this in more detail and see what the effects of that are. So here we are coming back to looking at the Earth right before what's called the summer solstice. And we can see the Earth rotating around that yellow line. And what's interesting here, if you look up here in the north throughout the course of a day, the sun is never setting. Inside this green circle, which we call the Arctic Circle, at the summer solstice, the sun never sets. That's pretty interesting. Now, there's another spot a little further south called the Tropic of Cancer. And at the tropic, at the summer solstice, the sky is vertical. If you look down here to Antarctica, in the area around the South Pole, at the summer solstice, you'll notice the sun never rises. So we can draw another circle here called the Antarctic Circle. At the summer solstice, inside the Antarctic Circle, the sun never rises. Now, take a look down here at the south. If you're just outside the Antarctic Circle, you'll see the sun rise and then set really quickly. And it gets very close to the horizon and then sets again. So you have these really short days in the south near the Antarctic Circle. In the north, you have the opposite effect. The sun rises and gets quite high and then sets. And the nights are very, very short. So at the summer solstice, at the north, light, at the south, dark. Now, the next important event we're going to talk about is what's called the fall equinox. This is when we're a quarter away around. And now what's going on? We see the sun just setting at the North Pole. So this line is the line from sunrise to sunset. Now, actually everywhere on Earth, you have 12-hour days. The sun is rising at the same time everywhere and is setting at the same time everywhere. You have the sun vertical at the equator on the summer solstice. At the fall equinox. In Antarctica, you see the same thing going on. Now the sun is rising at the South Pole, and everywhere else you have these same length days, these 12-hour days. So that's pretty cool. The fall equinox. So let's rush on now. Yeah, you can see it, the whole thing. At a given longitude, the sun is rising at the same time everywhere. Let's rush on now to the winter solstice. And now we see what's changed. Now in the north, here inside the Arctic Circle, it's constant nighttime. Just south of the Arctic Circle, you have these very short days. And as you go further and further south, the days get longer and longer. Now the sun goes vertical at what's called the Tropic of Capricorn, which is there. The sun is vertical at noon there, or solar noon. And then we go to the south, we see inside the Antarctic Circle now, it's constant daylight. And just outside of it, you get these very, very, very long days. So as you get closer and closer to the Antarctic Circle, at the winter solstice, the days get longer and longer. Another name for the winter solstice would be the austral summer solstice in Antarctica, or sorry, in the southern hemisphere. Okay, so you see that effect now. Now we're coming on toward the spring equinox, and we can see the sun getting closer and closer. And finally, at the spring equinox, we see sunrise at the North Pole. We see the days again, all 12 hours long, and we see the sun vertical at the equator, and we'll see the sun setting in Antarctica. There's the sunset in Antarctica. So that is a cool effect. Now, when you're in Antarctica during the summer, so here we are moving back toward the summer. We saw now the Arctic now gets completely sunlight again. I've been in Antarctica during the austral summer or the northern winter. I've been in Antarctica at the winter solstice, and it's a very weird thing to have the sun up all day. It just goes around and around in the sky, never sets. Very, very cool, kind of a fun thing. Okay, so moving on. We kind of understand how the seasons work now, don't we? Let's put it together. We've got the Earth. The Earth is rotating around an axis that goes between the North Pole and the South Pole. In fact, that's the definition of the North and South Pole, the points around which the Earth is rotating. The Earth is rotating, and the axis of that rotation is always pointed at the same spot in the sky. The Earth is orbiting around the Earth, and as it orbits, that point keeps pointing in the same place. And so, depending on the season, sun is shining more in the north or more in the south. In the summer, the sun is shining more in the northern hemisphere. In the winter, it's shining more in the southern hemisphere. In the summer, you can have very long days as you get closer and closer to the North Pole. While in the southern hemisphere, your days get shorter and shorter as you get closer and closer to the Antarctic Circle. So we understand seasons. We understand the motion of the sun. We understand why days are longer in the summer and shorter in the winter. That's really cool. So let's go on now to talk about the other thing we see in the sky, namely constellations. Now, this is kind of cool. Constellations. Now, when we look at the sky at night, you can sort of see patterns in the sky, right? So you look at these like, oh, that looks like an X. Or you look at this like, oh, that looks like some kind of shovel that can pick up water. Or you see these patterns in the sky made from stars. So people have been noticing these patterns for thousands of years and have come up with things on them. For example, we can imagine drawing lines between the stars to make these various patterns. So here we have, and we can imagine what these pictures might represent and give them names. So these are the Western constellations. They have their origins in ancient Greece. So there's some of these, maybe if you're from the West, you'll recognize some of these names like Ursa Major and Andromeda and Cetus and whatever. Okay, these are the these are the Western constellations, patterns of stars that people have observed for thousands of years, and these date back to ancient Greece. There are other patterns, of course. You can imagine the Chinese have a completely different pattern. And if you grew up in China, you'll say you might not recognize these constellations. Same stars. These are the Chinese constellations. Completely independent history. So there weren't people coming back and forth and saying, oh, this should look like something. And they see something completely different. They show completely different patterns than the Western constellations. Which ones are right? Both? Neither? Depends on who's writing your test. I don't know. Chinese constellations compared to the Western constellations, very, very different. The constellations patterns developed in the Americas were completely different than either those in Europe or Asia. Again, completely different patterns. They're seeing different patterns in the sky. There's the ancient Babylonian constellations. Actually, this set of constellations is probably the oldest known. This particular set of constellations dates back to around 1200 BCE, so 3,200 years ago. Again, independent of any of the other three we just looked at. So different cultures at different times have come up with different sets of constellations. these patterns don't really, well, science doesn't think these patterns really mean anything. These are just stars in the background, and our eyes see shapes, and we draw lines between them. Some people believe they mean something, but science as a whole would say, no, it's just a pattern that your eyes see. Okay, but we think we see different patterns at different times during the year. Can we try to understand that? So let's go back to this program we saw before, solar system scope again. And we see here we have the planets orbiting the sun in the inner frame, in the inner solar system. And we see in the background all these constellations. Here's all the constellations you can see. And you might think, well, they should all be visible at the same time from Earth, but that's not quite right. If you have the Earth here we have the Earth, and let's say you're on the far side of the Earth where it's daytime and you're looking past the sun, you would see these constellations, except you can't, because when it's daytime, the sky is blue, so you don't see those constellations. On the other hand, if you're on the far side of the Earth over here, the side far away from the sun, you're looking at night, you're looking that way. At night, you're going to see all these constellations. This would be now, sometime around September. So now if we go forward, let's grab it and go forward. Come on, go forward. Go forward 6 months or so. Now it's the opposite. Now the constellations you could see at night would now be up in the daytime, and so you can't see them because the blue sky is in the way. On the far side of the Earth, away from the sun, now the constellations that previously you couldn't see because it was daytime, it's now night, and you can see them. So the constellations you can see depend on the time of year. And that's pretty cool. So, wow. So we now understand the pattern of the constellations. We understand why they change during the year. Now, there's another thing people like to talk about. Sometimes people talk about what sign you're born under, what constellation were you born under. So we can try and go here and move this to, I was born near the beginning of May, so move this to where it would be near the beginning of May and see what constellation is the sun in. When I was born, the sun was in Aries. So I would say that my sun sign, this is kind of popular, what do you call it? Astrology. They say my sun sign will be Aries. And it's not really, because the Earth's orbit wobbles a little bit and it should be Taurus, I guess, but it doesn't matter. So I would say, okay, I was born when the sun was here, and therefore I'll have these, some given personality traits. So this is what we're talking about, called astrology. Astrology makes the claim, Western popular astrology claims to be able to determine personality based on where the stars and planets were when I was born. And this tradition goes back thousands of years. It was a hugely popular thing even in Roman times. The question is, does this work? Does Western popular astrology actually predict things about your personality? Well, if you believe in astrology, you'll think so. So I could go and read what astrologers say I should be like, and I might say, oh yeah, that's like me. Yeah, I get angry sometimes, or whatever personality traits I supposedly have, but the question is this real? Like, is it better than just a guess? So, there's been some so in science, you say, well, let's try to actually test this. So there's an example of what you might do to try and decide, does astrology actually work? Not astronomy, astrology, using the position of the stars to predict something about my personality. Well, they did a double-blind study. Double-blind means nobody knows the right answer. It's all hidden by the computer, and then you look at the answer at the end. What you do, astrologers are given the time of birth of a bunch of people, and they're supposed to say things about their personality. So they're supposed to write down, this person would have this personality because they were born at this time. And then a bunch of psychologists interviewed a bunch of people and did personality tests and determined their personality traits. And then they compared them. What do the astrologers say about the personality traits? What do the psychologists say about the personality traits? Are they the same? The answer is no correlation found. So what that says is either personality tests don't work, or astrology tests don't work, or both. Now, there's other tests that have been done that show that personality tests really do seem to work. So the conclusion here is that at least the astrologers who were interviewed, there's like 28 of them or something, these astrologers were unable to actually predict things about a person's personality based on when they were born. So there's other stuff that astrology claims. Another claim of pop Western astrology is that horoscopes claim to be able to predict events in daily lives, tell you about, give you advice, and tell you things about are happening with you in a day. And again, large studies of these claims have failed to beat random chance. Now, this is actually a bit of a tricky experiment to do. It turns out there's a lot of people who do feel that astrology works for them. And we can kind of understand what's going on here. If you read a horoscope and it says, you're going to meet somebody interesting today, and you believe in horoscopes, you'll say to yourself, hey, that person I met on the bus was pretty interesting. So it confirms your belief in the horoscope. On the other hand, if you don't believe the horoscopes work and you read this thing about meeting something interesting on the bus, you might say, yeah, but that person I met on the bus was really boring. So it's really hard to just look at a horoscope and decide if it's working or not, because you can read things into it. You can kind of say, oh yeah, I agree with that, or no, I don't agree with that. So in order to actually do this test, you have to do what's called a double-blind study, where nobody knows what the right answer is until afterwards. So a way you might do this is to have a bunch of horoscopes. Some of them are real horoscopes and some of them are fake horoscopes. And then have the person reading the horoscope read it each day and mark whether or not it worked or not, and see whether or not the real horoscopes did better than the fake horoscopes, for example. Any kind of study like this has been done has failed to show that it's any better than random chance. So the conclusion from it, that's how you kind of approach these things from a scientific point of view. There's a claim. Horoscopes claim to be able to predict events in daily life. You do the experiment, and then you conclude about whether or not it works or not. Now, you might go into this saying, I don't think they work. And then the person might go in and say, I think they do work. A good experiment shouldn't care what the experimenters think. And that's a hard thing to do. But whenever you're doing in science, you're always trying to come up with an experiment that doesn't care what I think. And that way, my biases or your biases won't come into the result. So when unbiased studies have been used to try and evaluate horoscopes, so far, they've shown that they're not better than random chance. Does this mean that all horoscopes don't work? Nope. All of the horoscopes that have been tested don't work. So there's that. So this has been really fun. We've gone and we've looked at the rotation of the Earth and seen how the rotation of the Earth can affect many of the things in our daily lives. The rotation of the Earth causes the sun to rise and to set again. The rotation of the Earth causes the stars to rotate in the sky. The rotation of the Earth combined with the orbit of the Earth yields more of the things. Because the Earth's orbit is because of the Earth's rotation is tipped compared to the orbit, then in the summer, light is shining more toward the northern hemisphere and it's warmer. The southern hemisphere is either shadowed or at lower sun elevation. So it's winter in the southern hemisphere, summer in the northern hemisphere. 6 months later, it switches around. Now the light is shining directly on the southern hemisphere, which is now warmer, and the northern hemisphere is cooler, summer and winter, caused by the rotation of the Earth and the orbit of the Earth around the sun. Similarly, because the Earth is rotating and orbiting, which constellations you can see at night change. When the sun is up, the constellations that are also up at that time of day can't be seen because of the blue sky. 6 months later, the sun is up at a different time, and therefore you can see those constellations. So we can really understand a whole bunch of things by understanding the rotation of the Earth and the orbit of the Earth around the sun. It all starts to make sense. So the next time you're out enjoying a beautiful sunset, think about the rotation of the Earth, and we will see you next class.